Hello, everyone. This is my talk, using change streams to keep up with your real-time data. It's going to be an introduction to change streams, as well as using them to turn MongoDB into a real-time data provider. Before we get into the meat of the talk or any introductions, I want to start with a personal story. This story is about how I and hundreds of other people wasted over an hour in the freezing cold of early March because of a failure to deliver real-time data. This all started on March 8th of this year. The day before, we had Winter Storm Quinn in the northeast US, which brought with it about 3 inches of snow. So naturally, a lot of people's commutes were disrupted, and I was no exception. At the time, I commuted from central New Jersey, here, to New York City by train. This was a 60-minute express train, and 90% of the time, things went pretty smoothly. But 10% of the time, things failed spectacularly. So naturally, the morning after the storm, I wanted to check for all available information to make sure there are no delays or cancellations. I go to the train service's website, where they have alerts and advisories, and to my pleasant surprise, there was nothing. I go to the train service's Twitter account, and the most recent tweet I see is that the train line service is operating on a regular weekday schedule. This was at 6:33 a.m., and here's a timeline. I see this tweet at 6:33 a.m. My train is scheduled at 6:54, so I figured how much could go wrong in 20 minutes. I arrive at the train station at around 6:45. I go to the train platform. It's below freezing outside, so I'm pretty anxious to get on the train. My train is scheduled at 6:54, but I wait for about 15 minutes, and no train has come at this point. Not too worried. I figured there might be some residual delays, despite the lack of warning. But then another 15 minutes goes by. More people are getting onto the platform. I start to get a little worried, so I go to investigate. I go into the parking garage and see a monitor like this, which some of you might have seen if you've gone through Penn Station. It just lists the trains, their times, and their status. So I see my train listed, and it just says delayed, which is no help to me, because I know it's delayed, because it hasn't arrived yet. So more time passes. I keep checking this website for alerts and advisories, and there's still no alerts or advisories. At this point, it's freezing outside. My extremities are starting to go numb. I really want to get on this train. More time passes. More people than I've ever seen before on the train platform waiting with me. I keep checking Twitter, but the most recent tweet I see is the one at 6:33 saying everything's okay. And then finally, a full hour after I got to the train station, out of the darkness, someone comes out and announces to the now overwhelmingly large crowd that the trains are bypassing the train station. The trains aren't stopping at our train station. And sure enough, I go back to Twitter, and I see a tweet confirming this, tweeted at 7:59. So at this point, I had a decision to make. I could either go home and work from home for the rest of the day, or I could go to the other side of the tracks, take a train going in the wrong direction to get to the next station to take a train going to New York City. The story doesn't end here, but I'm going to end it here. All said and done, I left my house at around 6:30 and got to New York City at around 11. But what really bothered me about this story was the hour between 7 and 8 o'clock. Because at this point, trains were bypassing our station, and our train service knew this. The train engineers knew not to stop at our station. But they never passed that information to the people that it mattered to most, the commuters who were waiting without any information. And I feel like this is a common problem with any complex service. There's some ecosystem of applications all relying on changes of state and data, but they don't always get in sync. And there's no better way to listen for updates from the data than to listen to it directly from the data itself. And this is exactly what change streams provide. This gives you a stream of updates directly from MongoDB. So it's about time I introduce myself, although it's already been done. But my name is Albertson. As was already introduced, I I work on the C and C++ driver at MongoDB. So let's actually get into the main topic of this talk. Here's what it looks like to create a change stream in the Node driver. It's only 2 lines of code. The first line uses the train collection, calling the watch function, which establishes a change stream. Since this is Node, it's callback based. We can say on a change, call this function. If this is, say, PyMongo or the Java driver, you would get a cursor, which you can iterate with .next. But since this is Node, we can use a callback. And all we're doing here is logging every change to the console, every change just being a BSON document. Here's an example of what one of those documents looks like. This represents an insert that occurred in this collection. And just as a disclaimer, even though this MongoDB world represents the 4.0 GA, change streams for collections have been around since 3.6, but they have made improvements in 4.0, which we will discuss later. So let's get into some of the characteristics of change streams. What kind of guarantees does the server make, and what do they look like? And for those of you who are familiar with the op log, you might be thinking, why should I use a change stream if I could just tail the op log? It's really these guarantees that make it a no-brainer to use a change stream instead of tailing the op log. To start, change streams use access controls. In 3.6, we introduced a change stream privilege action, which comes by default with the read role. So if a user has a read role on a collection, they can create a change stream on that collection. Since it's a separate privilege action, we give you the flexibility to create a custom role, which you can put read operations on that role, but excluding change streams. Second, we present a defined API. Internally, change streams use an aggregation stage, but all drivers implement a language idiomatic interface wrapping around change streams, which we saw before with .watch. And this is something MongoDB promises not to break in the future. This is something you rely on. And additionally, change streams scale across nodes. You can create change streams against any data-bearing node, whether it's a primary or secondary. And the goal of the project was to allow 1,000 change streams per data-bearing node without any performance degradation. And if you need to scale that further, you can use some kind of middleware. Change streams return 5 different operation types. Most of these are pretty self-explanatory, especially insert, update, and delete. Replace just means everything in a document has been replaced except for the primary key. You can think of it as if that document is deleted and then another was inserted with that same primary key. And invalidate is the only change that occurs without a real data change. This just means your change stream no longer makes sense to have open. This can happen if you're watching a collection and that collection gets dropped or renamed. Additionally, in MongoDB 3.6, we introduced a global logical clock, which allows us to order all of your operations across your cluster. So for example, suppose an operation comes into shard 2 here, then shard 3, then shard 1. MongoS has enough information whenever it gets those operations to reorder them in the correct order. And this is actually really important for change streams, because this means if you have 2 independent change streams from different clients, they will receive changes in the exact same order. Additionally, change streams will uniquely identify the document that is the subject of the change in this document key part of the change. The only thing worth noting here is that in a replica set, _ID is enough to uniquely identify a document, but in a sharded cluster, we don't actually enforce that _ID is unique across 2 different shards, so it is possible to have 2 documents with the same _ID in 2 different shards. So the document key in a sharded cluster contains both _ID and the shard key. Additionally, changes returned by a change stream are durable. They are majority committed, and you don't have to worry about them getting rolled back. So let's see what I mean in an example here with a 3-node replica set, the primary being in green and the secondary is in blue. So, and we have a change stream watching from the primary at the bottom. So a write comes into the primary, and at this point it's not eligible to be returned in the change stream because it's only been committed to 1 node. After it gets replicated to 1 secondary, it is now eligible to be returned in the change stream. and it also gets replicated to the other secondary. Because of this, if there's a failover, you don't have to worry about this operation having been rolled back.
Why is that exactly?
Because if there's a failover and you already have a majority committed operation, then a majority of the nodes will have seen it, so the new primary is guaranteed to have known about that operation. But you can ask again in QA part. So change streams are also resumable, meaning if it gets disconnected, it can reestablish itself and start listening where it left off. So for example, suppose the primary goes down, a new primary gets elected after the connections get closed, and we start taking writes again in the new primary. This gets replicated. Now our client has received a disconnect for this change stream. However, the most recent document the change stream received has a unique resume token on the underscore ID. The client is able to reestablish its change stream passing this resume token, and it'll get every and all changes that have happened after this. So we reestablish the change stream, and we get this new change that we would have missed. And it's worth noting that drivers will automatically resume once if it considers the error a transient error, like a network error or most server errors excluding a few blacklisted ones. So even though drivers will resume once, you can still access this resume token yourself and do your own retry logic. For example, here, on a change, we're caching the resume token from the change by storing the underscore ID. And on an error, we try to reestablish the change stream using this cached resume token. Now, the driver will automatically resume once, so this has the effect of resuming twice on resumable errors. Finally, change streams also allow you to specify a subset of the aggregation pipeline to do some pre-processing. You can push some of the work onto the server. For example, if you were only interested in a subset of a collection, maybe you were only interested in changes of like a few documents in your collection, you can use a $match stage to filter out a lot of changes that would otherwise have been getting returned to your change stream. Or in this example, we're using $match to only receive changes that are deletes or replaces. So these are the main characteristics. We have access controls. We have the separate change stream privilege action that we can use to create a custom role. We have a well-defined API, which drivers all implement their own language idiomatic interfaces. We enable scaling by allowing you to create change streams on any data-bearing node. We have this total ordering guarantee, which means that any two change streams will see changes in the exact same order. Changes that you receive are durable, so you don't have to worry about them getting rolled back. Change streams are resumable, so if there's a disconnect, drivers will automatically attempt to resume once, and you can implement your own resume logic. And you can also specify a subset of the aggregation pipeline to do some pre-processing. So we've talked a lot about the characteristics of change streams and shown a couple examples of creating them. I just want to get into one example of what it looks like in its full glory. This is the node drivers watch helper. First argument is aggregation pipeline. The second argument is a list of options. There's only one I really want to point out because it's going to come up in a few slides, which is max await time MS. And the reason I want to point this out is because, or I already said that, because we're going to see it in a couple slides, but what it does is it's the maximum amount of time the server will wait before returning an empty response. And if you are, say, using a driver that returns a cursor and you do next, this is the maximum amount of time it will block before returning empty results. So now we're going to get into the types of changes that a change stream can return. And for this, I wanted to make it something that anyone can try on their own. So you can imagine that you have MongoDB 3.6 or newer running in the background, and you have two shell windows open. On the left-hand side, we say db.collection.watch to create a change stream, and we pass max await time MS of 30,000 milliseconds or 30 seconds. And this is just to make it easy to see the changes appearing in this shell as we do something in the other shell. So after we do the insert in shell 2, what we'll see in shell 1 is a document that looks like this. The underscore ID is that resume token. The operation type is insert. NS, which is a namespace, has both DB and call because we're watching on a collection. We have a document key uniquely identifying this document, and we have the full document, which is the entire document inserted. So pretty straightforward. Update looks a bit different. Instead of having the full document, at the bottom we have update description, which contains both updated fields and removed fields. And the reason we don't have the full document available is because changes really come from oplog entries, and the oplog entry for the update does not contain the entire document that got updated. So if you actually need to access the entire document that was updated, you can use full document update lookup as an option to the change stream. And what this does is it will add the full document to the change, but there is a distinction. This lookup occurs at the time the change is returned, not at the time the change occurred. So for example, what could happen is, say you have two clients and they're both creating change stream, or client 1 is creating a change stream and client 2 is doing updates. So client 1 creates a change stream with update lookup full document. Client 2 updates the document setting X to 1. Before the server gets to return to client 1 this change, client 2 does another update setting Y to 2 as well on that same document. When the server returns the change of the first update to client 1, the full document will have been looked up at this time containing both changes. So it's something to keep in mind that this full document on update lookup is looked up at the time the change is returned. Replace is more of the same. Instead of an update description, we have the full document available because the entire document was replaced. And delete is even less interesting. It has less information. It's just a document key. And finally, invalidate, which is the shortest of all, just has underscore ID and the operation type. And at this point, you know that the change stream is no longer makes sense to keep open. So I want to briefly discuss the new changes to change streams in 4.0. First, as I've said before, change streams keep track, or at least drivers keep track of the most recent resume token on a change stream to resume a change stream. But now, change streams can resume before the first change is returned. Second, we can listen for changes on an entire database. And third, we can listen for changes on an entire client, excluding some system collections. So we talked about the characteristics, the types of changes that can return. Let's use what we've learned to build a simple application at a high level. In keeping with the theme, our application is going to show a real-time map displaying all train positions that we know about. Our collection is going to be super simple. It's only going to have two real fields, lat and lon, representing the position of each train. But we can imagine that these documents can get updated in multiple ways. Say, whenever a train arrives at a station, the train engineer does some manual signal to update the position with the exact known lat lon of the station. And maybe when the train is in transit, these documents get updated with some approximate GPS signal. We don't want to care about how these things get changed. We just want our application to have the most consistent view of everything in this collection. So our application is going to need to keep a cache of the state of all trains, all their positions, in the most up-to-date way. Initially, we're going to populate this cache, and we're going to do a find with read concern majority, so we don't have to worry about getting documents that could be rolled back. So to start, we just have one document. And then we create a change stream. To start, we will just use an empty pipeline and no options, and we'll see how far this gets us. So suppose we see a change, which is an update, and we see in the update description the latitude has been updated. Great, we want to handle this and update our application cache. But suppose the data changes, someone starts adding other fields to these documents, like passenger count. These are things that we don't really care about, and we're just wasting bandwidth receiving these changes. So we end up seeing this in our change stream, but we really don't care about it. So instead, we can use $match to filter out irrelevant changes. So here's our new change stream, including a $match stage on the pipeline, which can match on the update description let or lon existing. So we see that same change from before with the passenger count, and this time we correctly ignore this. We won't get this returned in our change stream. But maybe when a train gets commissioned, this is represented as an insert in the collection, and our current setup here will ignore this when it really shouldn't. So instead, if you're caching the state of all documents in a collection or from some query, you should handle all document changes. So our new pipeline has another $or matching a subset of updates that we care about, as well as any other operation type. So we see this insert again. This time we correctly handle it. We see a delete, and we also handle this as well and delete this from our cache. So at this point, we have an application cache that looks pretty much correct, except there is one problem, and that is in between the initial find when we populate the cache and the change stream that we create, an update could occur which we miss. And this could be pretty important, say if a train gets inserted between the find and the change stream, we won't ever insert this into our application cache, we might not show it at all. You might think we could just flip these operations around, but say if you are reading from secondaries, these might read from different secondaries and you can have the same exact issue. If the change stream starts on a newer secondary than the find, then the same exact issue can happen. So another feature in MongoDB 3.6 can save us, which are sessions with causal consistency. And I'm not going to go too deep into it, but causal consistency allows operations to see the results of previous operations. So what this looks like now is that a client starts a session, which by default has causal consistency enabled, starts a change stream. It could happen on any server. Server 1 and server 2 might be secondaries, or one might be a primary. The client does the find, and this is all on a session with causal consistency. Now, server 2 will wait and replicate up to the highest logical point of time that the client has seen thus far. So server 2 will replicate up to what it saw on the initial change stream, or what server 1 has replicated up to. And then finally, it will return that result set. So we're guaranteed that there could not be any updates in between the change stream, or sorry, in between the find and the change stream. And this is what that looks like in the node driver. We start a session. We just pass that session to our watch helper. We do a find, passing that session as well, and then populate the cache. And now, we have a consistent view of our collection in our application cache. Just build the rest of the app. It's left as an exercise. And here's our app. We have no rollback state because we read concern majority, and change streams also return durable changes that are also majority committed. We reduce bandwidth because we use a $match to filter out updates we don't care about. We handle network blips because change streams automatically resume in drivers once. We don't miss updates because we're using a causally consistent session. And it was super easy to prototype. Imagine having to do this without change streams you'd either have to tail the op log, which you really don't recommend and don't plan on supporting, and you miss out on these other benefits, or you'd have to pull the collection constantly, which is just unnecessary overhead for both the server and the client. And so I'm going to end that here and watch this nice animation, and I will take questions now.
You were showing how the line, sorry, we got the mics.
Great job on that. Had a couple questions for you. First off, when you were talking about the resume tokens, is that something handled by the client library if for some reason it lost connection? Does it reissue the connection and keep up with the resume token on its own?
Sorry, so the question was, does the client automatically use the resume token that is returned in changes? And the answer is yes. Every driver is required to attempt to resume once. So the driver will cache this resume token for you automatically. You still have access to it in your own application, though.
Makes sense. Thanks. And then the second one, and then I'll stop. I'll give this up. So, very synonymous to a pub sub system, essentially. We use Kafka today for a lot of pub sub needs, even considering moving some of our needs there to event streams or change streams. So one of the things that I'd like to understand is, in Kafka with Zookeeper, there's the concept of locking when you have multiple clients. Is there any kind of concept there, or is there any roadmap for such a concept where you may have 3 app nodes that are all listening on the same change stream, but you only want one to process?
So if I understand your question correctly, is there any concept of using one change stream and having multiple clients use that change stream? Not innately. You could build some middleware to do that, but not as it stands right now.
You were mentioning how the find command would generate a event in the change stream, and I was under the impression that since it is a change stream, any sort of modification, I don't know if I just misunderstood the phrase of what you were talking about.
Yeah, I might have just misspoken or not phrased it correctly, but the find command should not generate an event in the change stream. It'll just make sure when we use a causally consistent session that the server that we execute the find command on will replicate up to the same logical time the change stream server started on, if that makes sense.
So earlier you mentioned that you could have up to 1,000 change streams without degradation. Is that true? Or is that what you mentioned?
Yeah, that was like the initial goal.
Okay, and what type of other true throughput can you expect from this, and especially in a very high load service?
I don't know exact numbers, but more than likely, if you needed to scale this beyond 1,000 change streams per node, it's probably not the right approach to create additional secondaries just to do this. It's probably better to use some kind of middleware like Kafka. But yeah, I don't actually know what kind of throughput guarantees we give you.
Overall impact on performance with the implementation of change streams?
The question was, what is the impact of performance on change streams? So they will internally be scanning the op log. And in order to do that, it needs to bring op log entries into memory. So performance is going to be both bandwidth of sending changes to your change streams that are listening and also additional memory use from reading the op log.
is it possible to implement change stream on a server on a Mongo node itself rather than on a client, basically to use it as a trigger? So for example, if I have a capped collection,
Yeah.
which I keep at the certain size limit, and it basically truncates all the data, but I still want for the login purposes to keep all the data in a collection larger than this. Is it possible to implement change stream as basically as a trigger rather than something on a client listening for change?
As in, like, you have a change stream that is going into this cap collection, like saving all of the changes into it?
Now, as change stream that's listening for changes in the cap collection and inserting this data into some other collection.
I think that should be fine, but I think you'd have to do it on the client side. Like, you'd have to create a change stream on the client and then do those inserts into another collection, if I'm understanding your question.
Only for, right, so my main concern was if I don't want to bother client taking care of that, and if I want this implemented on a server as a trigger, basically, all my inserts are replicated into other collection, or all my updates are replicated into another collection.
Right. I don't know, I don't think that's possible right now, but you should go to the keynote as well.
Thank you.
You said that the change streams only report things that are durable. That's independent of write concern. Like in your example, read concern, sorry. In your example, read concern is only for getting documents, not for the change stream, right?
Right. Right now, change streams only use read concern majority to report those changes. Yeah.
Any other questions?
A follow-up to the performance question about change streams for each individual change to the database. Would you be able to actually, never mind, talk myself out of it.
Okay.
Thank you.
Any other questions?
I have a question, actually. What
Sure.
surprised you most about using the change streams? Like, yeah, were there any surprises to you?
Yes. This isn't something I mentioned in the talk, but one of the new options introduced in 4.0 is start at operation time. And I understood the start at operation time to mean that you can synchronize a find and a change stream starting like we did in the last slide or the last few slides by using the operation time that's returned by find to create a change stream, but that is actually not the case. Because operation time is a bit different from the logical cluster time that is returned in other commands. But yeah, that's not a great answer, but that's all I have.